Good afternoon, ladies and gentlemen. My name is Zijian Jiang, a postdoctoral fellow in Southeast University. My advisor is Professor Yamei Zhang. I'm very honored to have the chance to give this presentation and share my research with you. My research is in situ leaching behavior of Portland cement paste in different solutions. I have divided this presentation into 4 parts. Before my introducing the results, let me give a brief introduction about the research background. As we all know, the hydraulic structures and underwater constructions often suffer from leaching. The leaching of calcium from cement paste leads to the increase of porosity and loss of strength, in consequence affecting the long-term service performance of structures. To understand the effect of leaching on cementitious materials, researchers have done a lot of work using various testing methods. Here are some commonly used methods. From the micro level, people use MIP or XCT to obtain the porosity of leached materials, and using EDS and XRD to see the chemical composition change of leached materials. From the macro scale, people usually try to obtain the leaching depths and the mechanical properties of leached material. However, current methods cannot be used to obtain the leaching behavior of different phases. As we all know, cement paste is a complicated mixture of unhydrated particles, potentite, inner product, outer product, and aggregate. The leaching of different phases in cementitious material is a gradual process which involves in dissolution and transportation. It has been a challenge to accurately obtain the change of each phase during the leaching process. So far, there is still lack of intuitive results about the changes of different phases after leaching. Understand the leaching behavior of individual phase is the basis of leaching study for cementitious materials, so it is very necessary to develop a method that can intuitively reflect the changes of different phases before and after leaching in order to design durable materials. As we all know, backscatter electron image analysis is a commonly used method which can be used to identify different phases in cementitious materials, and the energy dispersion spectrum can be used to analyze the composition of different phases accurately. The combination of these two methods can be used to reveal the composition change of different phases after leaching. Based on this, we propose a new method to in situ observe the leaching behavior of different phases in PC. In this investigation, we mainly use BSE to do the characterization, so we need to prepare sample for BSE test. We polish the sample following this process. Here is the in situ leaching observation method we used in our study. Firstly, the surface of the sample before leaching is coated with carbon to enhance the conductivity. Then, certain areas containing representative phases are selected and marked on the BSE, and EDS is applied to analyze the composition of these phases. After the analysis, we will use the quick polishing to remove the carbon coating layer on the surface of the sample. After the surface treatment, the sample is immersed into leaching solution for 3 days and then dried in the vacuum oven. After the drying process, the surface of the sample is coated with carbon again. Finally, we will use BSE and EDS to in situ analysis the areas which has been selected and marked in step 2. Here are the optical images of the surface of sample before and after quick polishing process. According to the images, we can see that no cracks or obvious changes can be found on the surface of the sample after quick polishing, which suggests that the quick polishing process has little effect on the surface of the sample. Portland cement was used in this investigation. The water-to-binder ratio was 0.35. The sample chosen for the test was cured for 210 days. We used tap water for the mixing of cement paste and deionized water for the preparation of leaching solution. In this study, we used three different solutions for the leaching test. They are deionized water, sodium sulfate solution, and magnesium sulfate solution. The concentration of the sodium sulfate and the magnesium sulfate solution are the same. As we all know, the gray value can be used to distinguish phases vary in composition or density. In this image, the hydration products and unhydrated particles can be clearly distinguished from each other. This facilitates our further investigation about the leaching behavior of different phases. Firstly, let's see the leaching of PC in deionized water. Here are the BSE images of the same area before and after leaching. You can see that after leaching, the contrast and the gray value of the matrix decrease. C3S and CH, here the C3S, the CH, all disappear from the matrix and leaving holes in the matrix. C4AF and C2S still maintain integrity. Here is the C2S, here is the C4AF. They still maintain integrity. Inner product and outer product can still be identified in the matrix. Here are EDS results of PC paste before and after leaching. We can see that after leaching, the relative content of calcium in inner product and outer product both decrease, while the relative content of aluminum and silica in inner product and outer product increase. Then we analyze the composition of different phases. We can see that after leaching, the calcium to silica ratio of C2S inner product and outer product all decrease, while the aluminum to silica ratio of inner product and outer product increase, especially for inner product. The aluminum to silica ratio increased by 67%. Here are the BSE images of PC before and after leaching in sodium sulfate solution. Here is the image before leaching, here is the image after leaching. The contrast and gray value of the BSE image decreased significantly after leaching. The C3S and C2S are totally eroded and left holes in the matrix. It is worth noting that the layered structures here, the layered structures appear in the original position of C2S after leaching. Different from the phenomenon in deionized water, significant gaps can be found between inner product and outer product. C4AF still maintains integrity in the matrix. Here are EDS results of PC paste before and after leaching in sodium sulfate. After leaching, the relative content of calcium in inner product and outer product both decrease, while the relative content of aluminum and silica in inner product and outer product both increase. Then we analyze the composition of different phases. After leaching, the calcium to silica ratio of C2S inner product and outer product all decrease, while the aluminum to silica ratio of inner product and outer product both increase. This phenomenon is similar to that observed in deionized water. Here are the BSE images of PC before and after leaching in magnesium sulfate. Here is the image before leaching and here is the image after leaching. We can see that after leaching, the contrast and gray value of BSE image decreased significantly, which is more obvious than the previous groups. Different from that in deionized water and sodium sulfate, no obvious changes can be found on C3S and C2S. However, a lot of cracks appear in the matrix after leaching. Here are EDS results of PC paste before and after leaching in magnesium sulfate. we can see that after leaching, the calcium in C3S inner product and outer product all decrease significantly, which is more obvious than the previous groups. While the relative content of magnesium in C3S inner product and outer product increased significantly. After leaching, the calcium to silica ratio of C2S, C3S inner product and outer product all decreased significantly, which is more obvious than that in the ice water and sodium sulfate. The aluminum to silica ratio of inner product and outer product also increase, indicating that the dissolution of silica is faster than that of aluminum. Here is the change of calcium to silica ratio of C2S and C3S after leaching in different solutions. Among these three kinds of solution, the decline of calcium to silica ratio in magnesium sulfate solution is the highest. This should mainly be attributed to the substitution of calcium by magnesium during the leaching process. Here is the change of calcium to silica ratio of inner product and outer product after leaching in different solutions. Similar to the results of unhydrated particles, the decline of calcium to silica ratio in magnesium sulfate solution is also the highest. Compared to outer product, more reduction of calcium to silica ratio can be found in inner product, which should be attributed to the existing of ethylene in outer product, which is relatively insoluble. Here is a change of aluminum to silica ratio of hydration products after leaching. After leaching, the aluminum to silica ratio of inner product and outer product both increase, which indicates that the leaching rate of aluminum is slower than that of silica. Now we can come to the conclusion part. Firstly, this in situ observation method provides a new method for in-depth study of the leaching behavior of various phases in cementitious materials. Secondly, after leaching in de-iced water, the C3S and CH suffer from significant erosion, while the C2S, C4EF or outer product and inner product remained intact in morphology. Finally, compared with the sodium sulfate solution, the calcium in C3S and inner product decreased more significantly after leaching in magnesium sulfate solution, which should be related to the substitution of calcium by magnesium. That's all about my presentation. Thank you for your listening.